Okay, so arc length speed with parametrics is very similar to arc length with the coordinate grid. Okay. Who remembers the XY coordinate grid arc length formula?
1 plus f of x squared.
Square close.
Square root of 1 plus f.
Closer. There we go. Okay. Wow. So that would be an XY. That is arc length, right? We're going to get a very similar conclusion for parametrics, so you don't have to really remember much difference. It involves the derivatives of the x and the derivative of the y. Let's see what changed. So with parametrics, there you go. Okay, see the similarities? You can derive one from the other. This is, you can remember the Pythagorean theorem, arc length is very similar to that. Just keep in mind, if you have a parametric equation of some kind, they do tend to wander. Okay, so this equation will actually give you the length of that arc. This is also known as distance traveled.
How would you know, since it like arcs back on itself, how would you know which answer
Just
you
thinking that, so A and B gonna be different times instead of
They're,
position.
Oh, yeah.
they're different times. Yes. Yep. So that's the difference there with parametrics. So that is the difference.
So A and B are the time?
Yes, and that's what allows us to calculate the arc length when it comes back on itself. So the nice thing here is distance traveled in parametrics is enough. We don't have to worry about absolute value, right? Because in the XY plane, we have to worry about if it comes backwards, that will be an absolute value, right? It's negative velocity. Here we don't have to worry about that. Okay, so there is an advantage of parametrics. Let's just do an example here. You slide. Okay, I hey, there we go. All right. I like this program a lot better now that I've started using it again. Okay, let's look at the cycloid again. We're gonna check out a cycloid of radius 2. Remember that the cycloid of radius 2 is the trace carved out by a circle of radius 2. And I just thought of this morning. Why does it end at 4 pi? Why does it repeat at 4 pi?
Would be radius times 2 pi.
Yeah, the circumference of the circle is the radius times 2 pi, right? So 4 pi is the circumference of the circle. It's going to trace an arc that goes 4 pi units long.
Would you say it's also like the time it takes to complete one revolution?
Yes, these are values of t, right? Yeah, yes, that is a time interval. It's not the arc length, but it is the time interval. And it is, if you watch the circle at the bottom of the circle, it completes one revolution, so 4 pi units. Okay. So how could we calculate the length of an arc of a cycloid of radius 2? Any ideas? What's the arc length of a cycloid of radius 2? One arc. We'll just do it from 0 to 4 pi. Let me see how they're going to phrase this. Do you remember how to make these equations, first of all? What was the x?
Radius t minus radius sine t.
And the y was?
Radius
Radius.
radius cosine
Right. Those are in your book, but it's good to practice coming up with those on your own. So this is a cycloid that I just showed you on the wind plot. So we're going to go from we need the derivatives, right? That's what our formula dictates to us. X prime and y prime. We get what? Two minus 2 cosine b. Oh, much should have t on it. Two sine t. And we can set up our integral.
Wait, is y of t 2t minus 2 cosine t or no? It's-
It is off. Yeah, be careful there, because you were tempted to put a t with the new factors out. Okay, this is where we get a little messy. There's our integral. It's kind of ugly, huh? What are our integral limits?
0.
No. Actually. 4 pi is the circumference of the circle. Because the radius is 2. How much time has actually elapsed? 2 pi. Time is only 2 pi units, but since the radius is 2, the circumference is 4 pi. So those 2 pi units will actually go 4 pi. Does that make sense? 2 times 2 pi.
Is that what kind of standard or is it?
For a cycloid, it is. Yeah. You can also calculate it if you want. there a way we could calculate that out? Oh, you could set these equal to 0. and solve for Z. That would be your other way to do it, right? That would give you what the time is 0. So if you look at the graph, if you calculate when y is 0, that's when it hits the axis again. It should give you the time for your. That'll give you 4 pi over. Think about that one. All right, this integral gets kind of okay. You're gonna FOIL that out. You get 4 minus a cosine t plus cosine 4 cosine squared t, right? FOIL that out. And then plus 4 sine. And lo and behold, your trig identities finally start to pay off. Yep. Sine squared plus cosine squared is 1. If they each have a 4, it's going to be 4. So 4 plus 4, right? Is 8. Right, so if we rewrite our integral again.
Why would it be 4 plus 4?
Plus.
Well, I know, but what
Because
if
if you move,
if you distributed properly, right? It's 4 times cosine squared plus sine squared.
Yeah.
And cosine squared plus sine squared is 1, so it's 4 times 1.
Which is 4.
Yeah. So it's not 4.
Plus
But then
4.
have a plus 1.
there's a
Oh,
four
at
out
the very
front.
beginning. Okay.
Okay.
I thought you were saying at the end, that last part.
What?
was
What's
I'm
going
going
on here? Oh, I can give you one. Okay, this is, there's an identity for this. You rewrite it, and it's gonna give you a squared, so the square root goes bye-bye. The identity is, I think it's 1 minus cosine t over 2, and it equals sine squared t over 2. So is there a way we can write this here with that identity?
16 times 4.
So would it be
16
sine
Squared.
two over 8?
Right? The 16 divided by 2 is 8.
Oh.
And if you would distribute it, they're the same statement, correct? So now I can substitute. So. And now the integral falls out nicely. So. Yeah. It is actually one of the more obscure.
Okay, well, just because I also.
We did not address this identity in trig. You probably did not either. It's not a very common one. That's why it's given to you right in the problem. So it actually says it here. Use the identity recall the margin. That's where I get it. I would not come up with that myself. I would be like, well, how do we do that? Okay. But you can complete that, right? Good. The answer ends up 16.
we get like a calculator for these problems?
A lot of these would be calculator friendly. So we're not gonna expect you to recall these identities on the AP exam. You probably get to this point here, Math 9. Okay, but remember, this is parametric. You know how to do parametrics in a calculator. Okay. So go grab one. Go grab a calculator if you need to. Let's talk about it. Yeah, change your mode. Change to parametric mode. And then you do the same math 9, 0 to 2 pi, put your function in. Let's see if we can get what you want. Square root 8 minus 8 cosine t. Bam!
Yep.
We win.
Thank you.
So it's as simple as changing to parametric mode. It really is. Go into your what equals. Look at that. It gives you spaces for each x and y.
I tried plugging it in and mine wasn't working. And I don't know why. Right now I'm thinking about it.
You have a plot on. One of those highlighted.
My graph on the schedule of loss. So I just plugged it in and I did that.
You didn't change the parametric. No, you didn't.
Okay, there we go. I was missing.
What?
Parametric. Mode, scroll down to over to park.
I know, I'm already on it.
She got it. Don't worry.
I'm just saying, if my calculator's not. Yeah.
It's not good. Oh. Oh, here's what happens. You have to write your functions in terms of t. These transfer from function notation straight through into x. You have to change it to a
And then it
t.
works? Oh.
Circle, radius 30. All right? Good there?
Oh, it's great. Okay, flower.
You'll use it. Let's talk about speed now. Was that last equation not a position function? Yeah? So how would I find velocity from position? Derive it. Okay, so it's very similar. And I'm not going to walk through it here, the development of it, but it's very similar. The speed, because it's based in time, very familiar. It's the derivative of the integral, correct? So arc length has an integral. You derive that because you're looking for the derivative of position, and you end up with your speed formula. It's the same thing, it just doesn't have an integral on it. Okay, or you can think of speed as a rate. The integral of a rate is position change, right? Which is distance traveled. So they work very nicely in tandem with the ideas we've studied for the past year and a half. You can do, okay, let's talk about one example here and I'll let you loose. Okay, let's go with 2t and 1 plus t to the 3/2. Okay, what's the speed? And t equals 1.
Yeah.
The x prime of t is 2. This one is y prime is 3/2 t to the 1/2, right? You good with that? Okay, now evaluated at t equals 1. That one, of course, is going to stay the same. So we have our values to plug in here. So I plug 1 per time. Now the speed, we can also write ds dt. 2 squared plus 3 over 2 squared. And you can calculate that. Say 4 plus 9 over 4. 25 over 4, 5 over 2.
Wait, come on, so you're, when you derived y, it was 3/2 t.
Yeah, terrific.
Yeah, so where did the 1/2 go when you're, did that just cancel with the square?
I plug 1 in for t, because that's time 1. So 1, the square root of 1 is 1 times 3/2.
Oh,
So that's the number I'm plugging in.
okay.
Good. Speed is very easy because it's at a particular moment. You can just plug the number in that you're looking for time and plug the number in. And I believe it's 5 over 2. What are the units?
Oh.
Yeah, I didn't get any. So, there's one thing I want to, we can also do distance traveled here. Again, what's the translation of distance traveled?
Parametric
Arc length. Okay. Now, what if I asked you for displacement?
Just, couldn't you just do a Pythagorean theorem, distance from the end point to the start point?
Yeah, that's exactly what it is. So if you go, that's the major difference with parametrics. If you look at this original graph, okay, here's your starting point, and here's your ending point, right? Isn't that just a straight line? Yeah, this is just the distance formula.
Well, the distance between the first
Yeah. So remember your distance formula for displacement. Sorry, yeah, displacement. It's just a simple distance formula calculation. T equals 0 will generate a point, t equals 1 will generate a point, plug and chug. So parametrics actually a little easier with this distance and displacement. All right. Good to go?
They give you like the word, like, bottom of
one. Maybe not.
They're not going to. Could we? Yeah.
one.
Yeah, I think we could probably go there, but we're not gonna. I think I would probably confuse me at this point, because I have to look. Like, I'm about 3 days ahead of you guys on this stuff, honestly. I just finished 11-4. Okay, so,
1.5 have to be. Okay, don't have it. Well, I said people need to name their names.
Yeah, good luck with that.
That's all, they don't mind.
The human condition.